welcome to the last lecture of the course Industrial Robotics Theories for Implementation. Thanks for everything so far. You are now an expert learner of industrial robots who can now understand kinematics, dynamics, calibration, safeties and norms. With everything in place, now you need to run your robot to its full capacity. So let us begin with that in today's lecture, Industrial Robot Programming. So why do we need programming first of all? Programming is the only way to do fast, repetitive, monotonous and synchronous tasks. So you understand industrial robots, they are into tasks which are mostly quite repetitive in nature. Every second it is doing plenty good amount of tasks which are quite monotonous as well. If at all it comes to a person who has to do it, he may not be able to do it also. So let us say if it is tightening a bolt, whole lot of day it is tightening the bolt only, right? So every second you see it is picking up a bolt, putting it in place, tightening it up, right? Again for the next one also it is doing the same. Let us say it has to assemble a wheel. Maybe it has 36 number of bolts in a single wheel that it is to be tightened, right, for a truck. And you see it has similar things which are very monotonous in task, very repetitive, and it has to be done quite faster also, okay, and sometimes along with other robots also. So it requires a good amount of synchronization. So that is only possible if robots are programmed, okay. So that is the reason programming is very important. Same is the reason for programming to be there for any task which we do normally with the computers also. So the reason over here is similar. It lays the foundation to a successful robot deployment. If programming is capable of implementing quite good amount of features in it, let's say it can do circular trajectory by just single command, it can do a linear trajectory in just single command. If robot teach pendant, the programming tool, can suffice with all those instructions in place, you can do implementation in no time. So, and more precisely you can do it. Instead of defining a circle using points like that, it is better to have a parametric definition of circle within the compiler itself, within the robot interpreter itself, so that it can quickly create the code, we can quickly program it and we can use it. So having all those features in place, mostly industrial robot teach pendant, they have it. So that lays the foundation of successful robot deployment. It determines the capability of the robot. If a robot is capable to be calibrated by just touching a external tip from 3 different points and find out the tool dimensions, the way you saw it earlier in our chapter calibration. So you saw external point was placed in the robot workspace and you were made to touch the robot from different directions, and robot teach pendant, the controller can automatically identify the dimension of your tool. Similar was the case when you could identify the linear rail transformation matrix. So that makes the robot quite capable, quite much implementable for multiple applications, you see. Rather than having a raw robot which you can program through Python or any programming language of our choice, it is better to have an industrial robot which has all those features inbuilt to it, so that it makes it very capable for those specific applications. It drastically affects the deployment time. Having all those features in place, all the commands in place, all the calibration tools in place, everything is already inbuilt to your controller programming front end. So it affects the deployment time. You see, nowadays with flexible manufacturing system, you have very shorter lead times, right? Very scheduled, very tightly scheduled lead times. You see, you have to change your programming every maybe a month, every second week you have to change. So that is how, because your the type of goods it is manufacturing, that gets changed. It is very much customer specific. Even on a single assembly line on a Toyota plant, you see there are multiple cars which are getting manufactured. Multiple types of cars are getting manufactured in a single assembly line. Okay, you see, in those cases, in case of flexible manufacturing system, deployment time matters a lot. Your robot should be capable of handling such variations in your assembly line also. So that is just an application. There are many similar applications if it comes to industrial applications. So you see, that is the reason it reduces the deployment time drastically. Okay, it enables implementing reusable codes. If it is code, there can be various snippets of the code which are useful for various other purposes. Let's say you are taking data from a sensor, you have a filter which is there in place, and then it is handling something which is quite much maybe having a set of for next loop which handles quite a good amount of tasks. So the part of the code which handles the task and the part of the code which handles the filters are two different modules which can be clubbed with other programs also. Maybe you have a different set of tasks which is to be performed with the same set of sensors. So you may require the same filtering code again in some other code, right? So this is just an example again where you have two at least reusable codes which can be put to different programs, right? So this saves quite a lot amount of time and the effort that goes in it. Okay, and different modules of a task can be programmed by different programmer. Each programmer may be specialist of something else. Let's say in the earlier example also where I gave example of filtering a signal data which is coming from sensor, a programmer may be very much specialist in that. He will code for that particular filtering code, whereas a programmer who is very much expert in programming to do multiple things simultaneously using robot pick and place kind of thing maybe, so he may be given a task. So you see, multiple group of programmers can work together, do things in modules and put them all together to make a set of job handy, right? So that is the way it is programmed in industry also. It is not always a single programmer who does all the programming for any particular complex application in a system. Okay. So, however, the ease of programming with the teach pendant is a tool which comes with the robot controller. Okay, so that is the teach pendant. It has an integrated development environment IDE for any industrial robot is severely limited due to the complex hardware architecture of the robot controller. So it is not like a standard PC which does software programming and keeps it within. It has to be integrated with lot amount of external devices also, and those devices are many. Okay, and they are manufactured by different makers. Okay, so not like computers which has to handle just mouse, keyboard or a printer or a fax machine or something like that, right? So in this case, and hardwares are very complicated. Each and every hardware is very complicated. They are not updated the way it happens in software world, right? Not in as in case of our PC or a laptop. These architectures are very much constant for quite longer amount of time, okay, for longer period of time. So, and they are that makes things very complex. You see, you have multiple number of device, all has to be interfaced. Even the architecture of the robot controller is quite complex because it has to do things in real time. Time is very much crucial here, not like our laptop or a PC where handling a particular thing in a specific time, handling a trajectory is not there. Your time can run independently other than rest of the programs if it is there. That kind of complexity is there in case of industrial robot controller. Okay, so that makes this programming tool, that is the teach pendant, a very complex thing. And finally, when it comes to programming that programming cannot be developed, updated every second day. Got it? Not like our Android phone where applications are updated quite frequently. these architectures are not updated so frequently, and that is the reason, because of its complexity, it is very difficult to design a device driver for all the attachments which these kind of controllers are handling. So you see, it is very, very complex, and that is the reason the programming end is also very rugged, and it is quite much difficult to code in that. It is not as flexible as our standard C, C++, Python programming language, right? Although quite a lot of them are built over this, but the flexibility is a kind of very much limited. Just like as soon as you start typing, in case of standard IDE, it will automatically complete the intended commands that you want to key in. Those features are not there in case of industrial robots also. And mind it, these are made literally very simple, so that you don't need a very skilled programmer for industrial robots, right? So that is also one of the specific reason why industrial robot programming are made very simple, and it doesn't have too much of flexibility the way we have in our standard integrated development environment. The way industrial robot languages are evolved, we'll just go through that now. So first one was a wave that was developed by Stanford Artificial Intelligence Lab in 1973. They could integrate a vision system to demonstrate the hand-eye coordination of a robot. So you see, Stanford University has done quite a lot of job in robotics in those days when it was just evolving. You see, quite good amount of robots were evolved there. It was developed there. Finally, it came into industrial systems. Okay, so in those days, in 1973, Stanford AI lab was very, very developed, and they could develop such language, first language that was known as Wave. Then came a similar one that was based on ALGOL programming language in 1974. It was known as AL. It could control multiple arms, which could do cooperative manipulation tasks, designed to facilitate assembly operations using force sensor. You see, compliant manipulations, handling tasks using force sensor. Okay, so those kind of compliant manipulation tasks were the kind of research which was going on in those days in Stanford AI lab. Okay, and that is the reason this language was evolved also. They cannot just do pick and place tasks. So this type of assembly robots was force compliance, right? It was not just a standard robot which is position controlled. They were working on robots which were force controlled, torque controlled also. So that is one big area of industrial robotics, which is now termed as collaborative robots and cobots. Okay, so that kind of collaborative robot, it evolved from here only. Okay, next one is AML, that was developed by IBM, Thomas J. Watson Research Center, Yorktown Heights, 1982, a manufacturing language, AML. It is a high level language which has, you see, subroutines, which is there in our modern programming also. And it could manage assembly robots just like AL, and effectors, definitely, most of the robots that can do that, and active force feedback control. So this is again in line with this, and Cartesian arm, the gantry arm that I have shown you earlier while showing different kinds of robot and the classification. So you see, IBM has also come up with AML. It is not just in 1982 they have come up. They earlier had many other languages for their own system. Okay, RPL is yet another language, robot programming language developed by SRI International. It could do various machine of a work cell. Now the concept of work cell has come, okay, where it can handle robots, machine tools, vision system, and it is designed for non-skilled programmer. Now it is quite much of an attention was given to non-skilled programmer. Earlier days, robots were mostly used by skilled programmers, mostly who had very good advanced knowledge of industrial robots, programming, and intrinsics of the industrial robot, how it is made. When it came to industry, it was realized it is not going to be programmed all the time by those programmers, right? It has to be multiplied in numbers for industrial shop floor, and in that case such programmers were not readily available, so attention was given to non-skilled programmers also. Okay, next came the help that was developed by General Electric company. It was again an interpreter based language that was evolved over Pascal, that can handle multiple Cartesian arms in assembly tasks. So it is quite complex. It can handle multiple Cartesian arms and it can do assembly tasks. So it is quite advanced, you see. And then came NASA's JARS. So that was developed at Jet Propulsion Lab over there. This is again based on Pascal, used for controlling robots for the assembly of solar cell arrays by NASA. So it is very much specific to them. So it was not much commercialized after that. So MCL came later on, that is Manufacturing Control Language, that was developed by McDonnell Douglas under the sponsorship of US Air Force. This is again very specific to them. Extension of automatically programmed tooling, APT program, that is nowadays used for NC machines also. So it is just an extension of that. Okay, next came the rail, that was developed by Automatrix Inc. in 1981, again based on Pascal. You see, Pascal was a foundation for quite good amount of programming languages which is there. Okay, it is meant to control robot using vision. Vision is again there, incorporated with many constructs to support inspection. Right now, see, specific application add-on was there for arc welding system also. Right, so these are some of the advancements which was in line with modern day compilers or programming IDE that you see. Okay, VAL is the next one, Vector's Assembly Language in 1979. Later on an upgrade came in 1984. It was developed by Unimation Inc. that also developed the first robot, Unimation, right, and the Puma robot. This followed the structure of basic programming language, basic computer programming language. So it is not Pascal now. Okay, with robot motion commands, that is always there, that is to be there. VAL has its own operating system. Now the concept came for its own operating system. It is not just the programming front end, it is also the OS which is developed by the robot manufacturer now. It has its own user interface, editor and the file manager. So you see, it is in line with the OS and the complete hardware GUI that you can see in the robot's teach pendant. Whole of that is developed by the robot manufacturer. Okay, so this is one of the most modern one which is in line with the current day robot programming language also. Okay, and then this follows. So you have proprietary languages which were developed by KUKA. KUKA has its own language known as KRL, KUKA robot language. ABB has its own, that is known as Rapid Programming Language. Yaskawa has Inform 2. Fanuc, they have their own teach pendant with Carel programming language. Stobly uses Val 3 in line with this. So you see, other than a standard programming language which was developed over the years, proprietary languages took over. So each robot manufacturer, they came up with their own programming languages. Although the features were very much in line with them, it has its own OS, it has its maybe a collaborative real-time engine that runs behind, and then it has its own OS, or sometimes collaborative OS also they have, and then they develop the GUI in front of that. Like in case of KUKA, it has a real-time engine which runs behind with the front-end OS of Windows, and then it has its own GUI which actually does the integration of all these three. So user interface, editor, file manager, so everything is there in these programming languages also. So this finally took over, these proprietary languages. So there is no generic language which applies to all the robots. So they don't follow the way C++, C#, Python, it runs on all platforms. It is not like that. So in case of robots, each robot manufacturer, they have their own programming language. So it is very, very difficult to switch a user from one robot to the other one. If he is a specialist in one of the robot, he may not be equivalent in other robots also, right? It is very, very difficult. So this has to be evolved in modern years to come. Okay. So yes, the generation of programming languages as it evolved, the first generation language, they combined teach pendant procedures with the command statements the way VAL has. Okay, it has ability to define robot motions. Motion is the most important stuff which has to be there in any robot programming language. Mostly it is done using teach pendant to define locations. There are jog buttons. I'll show you how teach pendant look like also. So it has jog button which you can press and take the robot to a place. You can teach the robot that particular location, take it to that location, and create some statements to create some kind of motion sequences. Defined line, interpolation, branching, subroutines, elementary sensor commands to acquire digital and analog data inputs, right? Analog was not there with the first generation language. Okay, only digital input was there. Okay, next is the inability to use complex sensor data. It doesn't have ability to use complex sensor data. Limited communication ability was there with any external devices. Okay, it cannot communicate much with too many devices which are there in the industry. Okay, so second generation language basically overcome the shortcomings of the first generation language. They were more structured programming that was used, and added capabilities were made that made robot appear quite intelligent. Okay, that include languages like AML, Rail, MCL, Val2, etc. Motion control abilities were similar to first generation languages. Capability to integrate analog sensor has come. Okay, now you can use analog sensor also, not just the digital one, on off type of controller like proximity switches. It can also handle analog sensors like force sensor, pressure sensors, like. So ability to process information now and make decision based on the sensory information. So it has multiple if then else kind of commands which were there, so that you can, based on the inputs, you can control the robot. So that made robot appear quite intelligent over here, right? So ability to communicate with computers now. Okay, to keep the record of the data, generate reports, and perform motion control as well. Motion control is definitely the prerequisite. Apart from that, it can record the data on a PC which is connected to it. It can generate reports, how many bolts it has tightened to say. Okay, so yes, these are some of the capabilities which are there in second generation robot programming language. Okay, extensibility of the language is there. This language can evolve. It has provisions to include more commands through subroutines, macro definition, the way we do it in Python and all. Okay, so those features were also there in the robot programming language. So these are very advanced features which makes complex things to be defined in macro way, and then you just call that routine macro routine and it will just do that job in no time, right? Instead of writing the whole procedure every time, you can simply call those macros, just like subroutines. Hope you understand. So handlers to recover from faults. So it can also have handlers. If at all any fault occurs, it can do a set of job and stop the robot in case of any serious error, right? So those can be defined as well. Okay, so what should be standard functions of any standard programming language which deals with robot, right? So it should have instructions for motion control, that is prerequisite. It has to do those motions. How it is done? It can command for position. It can command for primitive motions like circle. It can generate lines. It can define a spline, right, by using control points, and maybe a standard cubic spline can be fitted. So that spline commands are inbuilt to this program. Instead of writing whole routine for the spline, which are really very complex, so it has an inbuilt feature in which you can define a spline also, and with different speeds. So on those paths, It can run with multiple speeds, okay, and in different calibrated frames. You see, you have, if you can calibrate your tool, you can take the tool tip to any trajectory. You know that already. That is the reason why we calibrated industrial robot earlier in one of the module. Okay, it can be calibrated to run on the world coordinate system, object coordinate system, workspace coordinate system, external circular rotary table you can use, right? So those are external frames that you can define and put that tool to move in that particular calibrated frames also. So that is what is motion control capabilities. That is what is desirable in any robot programming language. So instruction for tool control also, like gripper opening and closing, spot welding operation. So there can be add-on to standard programming language. Normally industrial robot, they come with a basic thing. Then depending on the applications, you can add on certain tools like spot welding thing, painting thing, right? So those add-ons can be added to create those features. Even to handle a gripper, sometimes there are gripper add-on to the standard programming through dedicated add-ons and the IO channels also, right? So tools can be controlled directly by IO channels or using those add-ons. Okay, standard programming instructions, what we normally feel we should be having those in our standard programming IDE. So looping, decision making, branching, if then else kind of statement, do while, for next, while, switch case statement, these basically increase the capability of the robot programming front end, right? Math functions like using sine, cosine functions, string functions, when it acquires data from a remote system, it comes like a string, and now you have to handle those strings. So string manipulation, that can be there in any standard programming languages. So there are standard instructions to do these kind of stuffs, right? So input and output instructions, like to handle digital and analog inputs if it is there, or output if it is there. So there should be ready-made command for that, right? You should not handle the straight away from the registers. Okay, you should have a mapped memory addresses maybe from where you can collect those data, right? Communication instructions, like to communicate through Ethernet and serial. These two are normally there in an industrial robot. Field bus communication is performed using mapped system variables or addresses. So field bus like Profibus, EtherCAT, Ethernet, so those communications, they can happen through mapped addresses, okay, where the data can be put and it simply can go from that address, right? So advanced functions are also there, like PID control. These are most widely used kind of controls which are there in industrial robots. So that is the reason, based on the input output relation, you can have a PID kind of relation. It has ready-made commands to handle signal filters, right? Butterworth first order filter to say. There can be a ready-made command where you have parameters to control the kind of filter you want. You can design your own filter based on the parameters, right? So these are some of the advanced functions which can be directly embedded in your standard programming language, or it may come like a add-on, right? So that is there. And miscellaneous commands which are there to control parameters settings. Let's say if it is a PID, you can have parameters to gain control, to control its gain, right? So there you have controller parameter setting, program selection, fault diagnosis. They are miscellaneous commands which are there, functions which are there in the standard robot programming languages, right? So you see, it looks like this. Standard programming front end is normally done on teach pendant. It is very, very inconvenient. It is to be held in hand, and you have touch screen sometimes. Sometimes you may attach an external keyboard, or this display can be replicated to any external bigger display with a keyboard, so that you can do programming the way you do normally on your standard PC. But that is not always doable in case of industrial software. You have to do programming over here only, because you have limited things to do. You cannot go and start programming genetic algorithm kind of complex thing over here. You don't need it actually in the industry, right? For research, this is not a platform to do research. There are other ways to bring out research using these kind of robots. I'll discuss that in the few slides to come. So it looks like very much like this. You see the programming. This is from KUKA GUI programming front end. It has, let's say, it has INI function. It has loop PTP, point to point, home, 100%, velocity to use, right? And then you have PTP to P1 location, velocity 100%. Data for that is stored in P.1. There are two files basically. One is the SRC file, that is the source file, which you can see here. And there is a file that is behind to this, that has all the data corresponding to the points that you have recorded, right? P.1, P.2, like that. So each robot has its own way of storing these data. With respect to tool 1, that is if there are multiple tools, you can call one of the tool as tool 1, tool 2. They are stored in the array. So over here it is tool 1 that you want to take it to point P1, and then you have base, which is defined here. So these are some of the calibrated tool and the base set in which you want to operate. So this is just an example I have shown here. So this is how it goes, and you can take the robot to different locations using the keys which are here, okay, in the teach pendant, okay. So even in case of Yaskawa robot, you see it has a similar front end which looks like this, okay. You have Z plus, Z minus, Y plus, Y minus, right, X plus, X minus, like that. So these are jogging keys. Similarly for roll, pitch and yaw, you can move them, right. This is to jog all these. There are menu holding buttons also with which you can handle the cursor, right. So this is the front GUI. You see it is very much similar to KUKA programming. MOV with velocity, and then you are handling on and off certain input, right. So it looks very much similar, and this is the front menu. You have gone to select the particular job, selected one of the job, that job is opened here. Got it? So this is a kind of menu I have just shown. This is with Yaskawa GP12 robot with YRC 1000 controller. So basically the GUI depends on the type of controller it is there, not on the type of robot which is connected to the controller. Okay. So mostly this teach pendant is a generic teach pendant for all Yaskawa robots, which can be connected with the controller YRC 1000. So there are other teach pendants also with other compatible controllers, okay. So this is an online programming. Online programming means a robot is connected live. You have to stop the robot and start programming, right. So there are other ways to do programming also, which is known as offline programming. So programming while the robot is already operating, right. You can program the robot while the robot is in use somewhere else, right. You can do the programming, you can dump that code to the robot when you are ready with the code, right. It is done with in an environment which is different to the intended program, right. The program may be there for some other application with some different set of environment which is there, right. Whereas this robot currently is mounted with a different environment. Your program may be for a different environment, right. So this is quite possible. So the robot is programmed on a virtual environment created using the CAD model or 3D scan data. So quite a lot of offline programming tools, they support 3D scan data also, right. So what are the capabilities which are there and what you can achieve with that? So let us discuss that. So planning the system and robot operation quickly and conveniently. So you see this is very convenient. While robot is already in use, you cannot program it. So you have to wait for that much time until your robot is off and you can program it. So you are saving time here. If you can do programming while the robot is already in use, you are saving time. You are doing programming in your own way. You are convenient mostly to do programming on the standard PC. So it is very convenient to program on your PC rather than on the teach pendant. So complex program can be generated. This allows optimizing different workspace layouts by running the simulation. So this front end, this offline programming system allows you to simulate the robot, see virtually how my robot will behave, right, what could be the best fit for everything, right? Where you have to locate the object, where you have to locate the tool set, right? So everything can be optimized over here. By rerunning those, you can see the one which has best optimized system of all the robot environment. You can directly deploy that to the robot, right? So it is easy to present. Now these front ends also allow you to create animated files like MP4 files or a GIF file, animated solution. This help you to present how you are going to make your robot work in the industry shop floor. Like, so in that case, you can show this animation to your customer. They will be impressed by looking at it, right? They can appreciate the thing better rather than explaining things in air, right? So in that case, this increases the success in sales and finally the revenue of a company, right? So it is easy to design the work cell concepts. In this case, you have multiple robots that can work together. So you have multiple robots here. Each one of them can be made with a different program. They can run with different program, and in advance you can make them do something, right? In advance you can analyze for its reachability. Collision tests can be done when all the robots will work, whether they will collide or not. You can easily check offline only without so it saves quite lot of hazard, right? So environment will be saved, money will be saved. If at all you can prevent any accident to happen, so this is very, very useful. You can make a micro motion study, right? When it will pick from here, it will put it there, how much time will go, how much time system is at idle state, right? So those can be optimized over here. So it has increased planning reliability also. It can do precise things with less cycle times also, right? So that is the benefits of having offline programming. Next is virtual commissioning. In this case, you don't just program the robot, you made it interface with maybe a real hardware somewhere, PLC connectivity, maybe with external access, with external sensors. Where the robot is in virtual, rest of the things can be in real, right? So those interfaces can be there, or even these can be there in soft. You don't even need that, right? You don't even need the PLC. You have whole set in virtual, right? And then you can generate your code and finally put it to use to verify the cell processes, to increase planning reliability again, and the safety also, right? So this is very, very important, and it is very much modular in nature. So existing work cell arrangement can be integrated with different applications. A robot with same kind of table with the same robot and a controller, right? You can have different things for this robot to do now, different tasks for this robot to do. It can be put for arc welding application, spot welding, punching. So whatever that comes in front of it, it can handle that, provided you can program it offline and dump them. So you actually, how it happens, you first program the way you program it. Instead of taking the robot to a physical location, teaching it, you just define a point as a parameter, and later take the actual robot to those location and teach that location. Got it? So you already have a code, a logic set, algorithm in place, and then you actually take those robots, jog it to the real location, teach those points, right? What you have put in your algorithm. So this is how it works. So that is, modularity is there. You can take a part of this code and put it somewhere else, the way we can do with multiple programmers developing a single program, right? So offline program generation for different robot controller combinations, right? For same program can be put for different robot with different controllers, optimizing energy consumption, right? So while doing so, you can even have tools that can optimize the energy which this robot will take up when it is actually put to use. So in long run, it saves quite a lot of revenue, right? So yes, there are definitely some shortcomings for this also. It needs some expert programmers and additional investment is required to buy these tools also. Offline programming tools are very, very expensive for industry. So yes, but with this you can save a lot of money and time. Definitely programming is a day-to-day job, but it is not very frequently done. So this can be used, right? So you can have a expert programmer here who can do one programming. This system runs for a while or for a few months, and then you can again call him back and do the next programming, right? So in that case it can be done, right? So there are various offline programming developers also, apart from proprietary ones which are mentioned here. ABB has its own robot studio. Yaskawa, no, it is known as MotoSim. Kuka Sim. Fanuc, it has RoboGuide. Stobly, they have 3D Studio. Mitsubishi, it has Melfaworks. Kawasaki has PC Rosset. Right, so there are various proprietary developers who are there. They basically make the simulation system for their own robots. So mostly you will have to be very much in line with these only, instead of open source and those tools. In industry it is not practiced because of safety reasons. Okay, although you have many other open source developers, it is not an open source. Here I mean is this can handle multiple robots of different make. Robot DK can handle ABB robot, Fanuc robot, right, many other robots, whereas Kuka Sim can only handle Kuka robots. So yes, it must be quite obvious these are inexpensive and it can handle multiple robots, but you cannot rely on them 100%. That is the reason industry, they don't go by these. They normally prefer using the simulator which is designed by the robot manufacturers themselves, due to the safety reason and the amount of cost which is involved in creating those industry systems, right? Delmia by Dassault Systems, Robcat by Technometrics, Cosimir by Fisto. So there are many open developers also. Yeah, programming with PC feature also using APIs. They are supported by many manufacturers, robot manufacturers. So they have API which can be called on any standard programming language like Python, C, C++, Visual Studio, and those kind of environment, right? So you can call these API and they have device drivers which can communicate with your standard robots, industrial robots as well. This again is not preferred in the industry, okay, due to again safety reason and real-time issues also. Okay, there are a few examples like Moto Plus SDK. It is by Yaskawa. ABB Robot Studio SDK. This is by AB Robotics. So you see there are a few which works like this also, and definitely there are advanced programming also, mostly used for cobots. Cobots, they have programming language which is very, very similar to standard programming language. They have APIs inbuilt to the programming they have, right? Like Kuka Iva, it has its own Sunrise operating system which is very much like Java, and definitely you have ROS, robot operating system. You must have heard of it. That is hardly used in any industrial soft floor because they are mostly for research purposes. So somebody who is interested in robots, using industrial robots for your research, you can definitely pick up few of these, right, from here to here, right? But in industry these are used. Okay, so hope you got the idea how industrial robots can be programmed, different ways it can be programmed, what all features that normally should be there, right, how it has evolved. So I think with this we can end today's lecture. In the next class we'll just have discussion on concluding the whole course, and today I'll finish this lecture and the course also. That's all. Thanks a lot for being with me.